The unit circle is a tool that we use in math in order to allow us to extend the domain of sine and cosine to any and all real numbers. And here's how you use it. At this starting from here, this would be a normal pi, or if you were to go all the way around 360 degrees, it would become 2 pi. But we're just starting at 0 degrees or no pi at all. All because we don't like it. Anyway, so every 30 degrees you would add 1/6 a pi, or yeah, 1/6 a pi. That being said, this would be pi over 6. This one would be pi over 4 because, pi over 4 because it's 1/4. Then this one would be pi over 3 because it's 1/3 and 2, or just 2/6. Now it's at 0 degrees, 30 degrees, 45 degrees, and 60 degrees. And it's this point, since this part is the origin, that means this point is 1, 0, and this point would be 0, 1, aka pi over 2, which is just pi halves, and thus 90 degrees. And then you just add each of these as you go on. So this is 2 pi thirds. Anyway, these pi over 2, 3, 4, and 6 all continue around the circle, going higher and higher. Once you're about halfway through the circle, or 180 degrees, you'll just have pi, and then you basically start all over again, only you're putting it at like one above the denominator. Now it's 7 pi 6, 5 pi fourths, 4 pi thirds, 3 pi halves, 5 pi thirds, 7 pi fourths, so on and so forth. And then finally, these numbers right over here are the coordinates and notice how far away from the origin point they are. This point I already said was 1, 0, and this point was 0, 1. And the spot in the middle, which would be pi fourths, would be the square root of 2 over 2, square root of 2 over 2. And those numbers would swap depending on where in the unit circle they are. For example, at 3 pi fourths, it would be negative square root of 2 over 2, and then square root of 2 over 2. So because it's basically just that's how far away from origin it is. So I'm just going how far this way, which would be cosine, and then how far up, which would be sine. Oh yeah, and then finally there's like 2 triangles you need to know. These are 2 triangles that you need to know. It's showing basically how we figure out these numbers over here. Yeah, because on one part it is, and more specifically, they're more for the numbers like square root 2. This is because it's okay, out one side, and then yeah.
So another important topic that we learned was the trig identities. So over here we have sine theta equals 1 over cosecant theta, and that's equal to each other, and it would be the sine theta is the reciprocal of this. And then the next one would be cosine theta is equal to 1 over secant, and tan theta is equal to 1 over cotangent theta. So when you're given a problem, it's important to use this so that we're trying to get it into terms of sine and cosine. And then down here we have tangent theta equals sine over cosine. So some other things that were given was sine squared theta plus cosine squared theta equals 1, and 1 plus tan squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. Over here we have how it relates to the unit circle. So sine theta equals y over r. So all of this is basically the SOHCAHTOA. So that sine theta would be opposite over hypotenuse. So if you looked at the unit circle, that would be opposite over hypotenuse. And then cosine theta would be x over r, and r is the radius. And so cosine, that would be adjacent over hypotenuse, so that would be this and this. And then tangent theta is y over r, or y over x, and would be opposite over adjacent. And over here we have the reciprocal of this side. And then this over here is just another important identity to remember, and that would be the limit as x approaches 0 is sine x over x, which equals 1, and that would equal x over sine x. And the limit as x approaches 0 is 1 minus cosine x over x, and that would equal 0.
Using these identities, we're able to look at the problems in terms of sine and cosine, which is good because in this problem that we'll present next, we're given points in terms of x and y, which is also equal to sine and cosine. So we're able to plug those points in and solve for the problem that way. So now we're going to use a problem to combine both of those ideas that we just talked about, the unit circle and the trig identities there. So and we'll talk about limits in this problem too, but later on in this presentation we'll have something specifically for limits. So for right now we'll just say that the limit as theta approaches 0 is going to be tangent theta over theta. So right off the bat, oh wait, okay, go back to that. And so then we're given this point of 1, 0, which as we explained before, this is given 1 is x, 0 is y, also known as 1 being cosine, 0 being sine. So the first thing we can do when we're given this is look at the trig identities and try to turn this tangent theta into something more workable, like the sine and cosine, because we're already given these 2 points and we're looking to plug these in. So if we go back to that, those trig identities that we mentioned before, we know that tangent is equal to sine over cosine. So we just rewrote this over here. So limit as as theta approaches 0 is sine theta over cosine theta. And then we just brought this theta over and made it theta over 1. That doesn't mean anything. It looks better when we're working with it. So down here, if we follow the arrows, we're just rewriting limit theta as approaches 0, and we're just gonna plug things in. So these points here, we're gonna use them now. So sine is 0, so we're gonna put 0 up here, and cosine is 1, so we have 1 here. And then we're gonna come back to this, so the limit as theta approaches 0, we're gonna plug 0 in for theta, and so that's why the 0 is here, and then we'll just bring down the 1 from here. So then we'll do the keep flip change, as noted by this arrow here, which will bring us over here. So we'll rewrite it again. Limit as theta approaches 0 is going to be equal to 0 over 1 times 1 over 0, because over here we had 0 over 1 and we had to flip that around. And when we solve for that, we find that the limit as theta approaches 0 is 0.
The definition of a derivative is shown as the limit as x approaches 0 is f of x plus delta x minus f of x over delta x. The derivative is a slope or rate of change in the value of a function. Specifically, the derivative at a certain point is the slope of the line, which is also the same as saying it's the slope of the tangent line to the graph of the function at a given point. So for problem E, we have a given table, and from this table we have to find the derivative at the point of 3. So to find the derivative, we actually have an extra amount of information, and we don't really need this point and this point. We just need to focus on this point and this point. And then, so when you find the derivative, you have to find the difference between each of these. So 2.999 minus 3 will give you negative 0.001, and then 3 minus 3.001 will get you negative 0.001. And then you find the difference on the other side, the y, and that would be negative 0.004999 minus 0, which gets you the same number, and then 0 minus 0.005001, which will get you negative of this number. The next step to finding the derivative at the point of 3 would be to take this number and divide it by the number you got over here, and this number divided by the number you got over here. So that would be negative 0.004999 divided by negative 0.001, and that'll get you 4.999, and negative 0.005001 divided by negative 0.001, and that will get you positive 5.001. And based on these numbers, you have to find the average. So 4.999 plus 5.001, that'll get you 10, divided by 2, which will get you 5, and that's the derivative of that point. Okay, so another topic that we learned this year was related rates, and it's basically everything we've learned in the chain rule, except now it's dealing with dx over dt, so the derivative with respect to time. So the problem asks, a ladder 25 feet long is leaning against the wall of a house, and then the picture's over there. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, and 24 feet from the wall? So over here, we're just gonna explain how to do it for 7 feet if the base was 7 feet. So the first thing you need to understand is the equation of a triangle. So that would be x squared plus y squared equals r squared. So it would be x squared plus y squared equals 25 squared. And based off of this equation, you're going to find the derivative of it. So use the power rule here. So that would be 2x. And since it's dealing with x, it's going to be dx over dt because we're finding the rate. And then plus 2y, and since it's dealing with y, it would be dy over dt equals 0 because the derivative of 25 is 0, or 25 squared is 0. And then, okay, so after we got this, it was given that the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So the dy over dt is going to be 2. And then after this, all you're going to do is solve for the dx over dt because we're looking for how fast the top of the ladder is moving down the wall when its base is 7 feet. So that would be dealing with the dx over dt. And you're just gonna, so the first thing you're gonna do is subtract the 2y times 2 on both sides. So that would cancel out and then be on this side. And then that'll get you to 2x dx over dt equals negative 2y times 2. And then to get this by itself, you divide 2x on both sides. And then you get negative 4y over 2x. Yeah, you get negative 4y over 2x. And that can be simplified to negative 2y over x. And that'll be dx over dt. And what we're looking for is it was given 7 feet. So you just plug in 7 into the y and then simplify after that. And after it's been simplified, you get 7 over 12 feet per second. Negative 7. Wait.
Okay, so next we'll talk about implicit differentiation. So this technique is used when the explicit form is not available, and we've been working with the explicit before this. So you'll see that in some of the other examples like product and quotient rule. But anyway, so implicit differentiation works with equations in respect to the x variable rather than the y, and can produce a derivative containing both x and y. So we'll see that as we go along here in the problem. When we're performing this strategy, we need to start by differentiating both sides of the equation, and so we'll do that right now. So the problem that we're given is here. So x squared minus y to the third power is equal to 0. So this is a little bit different than what we're used to, because in the explicit form, this would normally be a y over here, but this is not a problem, so we can just use the power rule to find the derivatives of these. So x squared comes to 2x minus 3y squared, because that's, if you do the product or the power rule for that, that's what you get. But something important for this implicit differentiation is that since you're taking the derivative of this and it's the y variable, you're doing it in terms of x, so you'll have to multiply that by 1 dy over dx, and then the derivative of 0 is equal to 0. So what we'll do now is try to get this section of the equation onto one side so that you can get dy over dx by itself, because ultimately that's what we're solving for. So to do that, we'll just add this 3y squared times dy over dx to both sides, and that'll leave us with 2x equals 3y, a positive 3y now, to the second power times dy over dx. And then we'll just divide both sides by 3y squared to get 2x over 3y squared is equal to dy over dx.
Okay, another thing that we learned in class was related rates, and for this problem it says that the formula for the volume of a cone is V equals 1/3 pi r squared h, and the question asks to find the rates of change of the volume if dr over dt is 2 inches per minute and h equals 3r when r equals 6 inches. So, okay, so here's the volume of a cone. It's 1/3 pi r squared times the height, and it gives you that h equals 3r, so you can plug that in for h, and then now you have 1/3 pi r squared times 3r, and then since this is all being multiplied, you can cancel out the 3's and it will equal 1, so that'll be v equals pi r to the third. And then the next step to do would be to find the derivative of the equation or the formula. So the derivative of v would be 1 dv over dt, and then you would use the power rule here. So it would be 3 pi r squared, because you're subtracting here, and then since it's dealing with r, it would be times dr over dt, and then after that you can plug in r, which they gave you, which was 6, and so you plug that in, and then it also said that dr over dt is equal to 2 inches per minute, so you can plug that in too. And then basically you solve for it, and you'll get 216 pi inches cubed per minute.
Okay, so for this problem, we're going to be looking into special derivatives and the chain rule. So the problem that we're given is e to the 4x plus 2 times natural log of 2x. So we see we have some product rule, we have some power rule, and we definitely have some special derivatives here. So first we're just going to break this apart because we are working primarily with the product rule here. So our f of x is just going to be this whole section here. We're just going to bring that down. And then the g of x is going to be this section here because they're being multiplied. So in order to find the derivative, to find f prime x, we need to do the chain rule because we can't differentiate this by itself. So what we're going to do is we're going to take this and bring it down to here for the chain rule section. So we'll just break it up even further. So h of x is going to be this e to the x, and then the k of x is going to be 4x plus 2, because this goes right in h of x where the x was. So to find the derivative of e of x, that's one of our special derivatives, which is equal to itself, e to the x, and then the derivative of 4x plus 2 is just 4. So in order to do the chain rule, we have to plug this k of x into h prime x and multiply it by 4. So we can see if we come back up here into our f prime x, we have this, 4e to the 4x plus 2. All right, so that one's done, the f of x and f prime x. Next we'll find g prime x when we're given this natural log 2x. Recording, okay. So we'll do another special derivative when we find the derivative of natural log of 2x. So the way we could do this and the way that we chose to do this is to break it up. So we did the natural log of 2 times the natural log of x. And this was easy for us because the natural log of 2 is constant, so the derivative of that would be 0. So all we would have to do is find the derivative of natural log of x, which for the special derivative would just be 1 over x. So with all of these, now we can plug it into the product rule, which is shown over here. So we did g of x times f prime x plus f of x times g prime x.
Go.
Okay, so from here, okay, because there's a lot going on here, we just ended up multiplying these two, so we just had this 3 to the 4x plus 2 over x plus all of this, and we just brought that down to here. So to simplify this further, so what we're going to do next is we're going to imagine that this and this are separate. And so we're going to multiply this side by x over x and leave this here. And so when we do that, we will have all of this over x times x. And then this will stay the same. So we can combine those two because they're both over x down here. So we'll take out this e to the 4x plus 2 from both of these, and we will multiply that by this 4x, because we just multiplied that by x, times the natural log of 2x plus 1 that was left over from when we took this out of this.
Okay, so the product rule is basically as follows. With the example that we were given, which was the derivative of f of x times g of x, and that would be equal to the derivative of f of x times g of x plus the derivative of g of x times f of x.
Okay, so the given function was x to the 5th times cosine x, and the goal is to find the derivative of that. So when you use the product rule, first you have to do the derivative of the x to the 5th. So that would be 5 times 1 is 5, and 5 minus 1 is 4. So 5x to the 4th. And you would multiply that by cosine x. And then after that, you would add it to the derivative of cosine x, which is negative sine x. And you would multiply that by x to the 5th. So when you write that out, that would be 5x to the 4th times cosine x plus x to the 5th times negative sine x. So the derivative of x to the 5th times cosine x plus the derivative of this times x to the 5th.
So quotient rule is another way to find derivatives, and for an example of that, it's given for the general formula of it. It is the derivative of f of x over g of x, which is equal to g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared.
So what we're going to do to start this problem is just identify the parts. So we'll have 4 parts here. The first is just f of x, which is this entire top part here. As you can see, this correlates right with that. And then we'll find the derivative of that. And so once you do that, you'll just find that that's 4. And then we'll have g of x, which is just this section right here. And then the derivative of that is what we found here. So this 1/2 x to the negative 1/2. And what we'll do next is just in this black here, we'll just plug everything in. So g of x is this, we'll plug that in right there. Then 4 is the derivative of f of x here, and so on until we have this entire thing written out here. So next we're going to begin to simplify, which is shown in the red here. So we'll just start out by noting that the denominator here is x, and we do that up here as well, because g of x squared, which would be this square root of x, if you square that, you'll just get x, which is what we did here. So that's what we did to start. Next, we just rewrote this because this looks a lot cleaner than this does, but same thing here, we just brought that down. And then we combine these two because they're being multiplied, which is what we have up here. So to do that, we'll just multiply this 4x by this, and then this negative 2x by this. So when we do that, we have this minus this, because this is a negative 2 here. And then we can go ahead and further simplify this. Simplify this down to this, and this down to this. And the way we did that is we played around with the 4 and the 1/2 here to get 2. And the exponent of x is just 1. And so to combine these two, we'll just get a negative 1/2. So this turns into 2x to the 1/2 power. Same thing for this. We have 2 and then 1/2, which is 1. And we still have that negative here. Don't forget to bring that down to the x, and then we just bring down that exponent here. And that's all over x. So once we have that, then we'll move on to this over here in the blue. So what we did was we took our work from here and just wrote each of these 3 parts over x itself. So we have 1, 2, and 3. What we'll do next is bring the x up to the top for each of these. So we'll multiply each of these 3 by x to the negative 1. And to do that, we have these 3 here. So we'll have 4x to the negative 1/2, because x to the negative 1 times 4x to the positive 1/2 is equal to this. And we did this for these next 3. Okay, so let's just explain that part a little bit more. So right now, over there we were given this, minus the 1 here. So it was just 4x to the positive 1/2 over x. And so I wrote this 1 here because this x is to the first power. And what we ended up doing was we brought this x up here, and we had to rewrite that as x to the negative 1, and we had to multiply that by this 4x to the 1/2. And in doing so, we add 1 to negative 1 to the positive 1/2 to get 4x to the negative 1/2. And we did that for the other 2 fractions in this step. And then we combine these 2 because they're to the same power. And we just brought this one right down. So in doing this, we have 2x to the negative 1/2 power plus x to the negative 3/2 power. So we rewrote this by bringing the x back down to the bottom. So we'll have 2 over x to the 1/2 plus 1 over x to the 3/2. And we're not done here because we need to keep simplifying. So what we'll do is multiply this entire side by this denominator over here, and then we'll do the same over here. And so when we do that, we have 2 times this, which is shown down here, and we'll have 1 times this, which is shown down here. And so we'll just add those together because we'll end up bringing these denominators together, which is what we did right here. So we multiplied this by this, and this by this, common denominator, and we threw it down here on the bottom. So once we have this, we can take it one more step further to simplify. And so we'll just bring these two together because x to the 3/2 power times x to the 1/2 power, we can simplify that by adding 3 and 1 to get 4/2, and we'll just rewrite that as x to the 2nd power. And this is our final answer. Okay, so for this problem we're going to explain the power rule and how to find the equation for a tangent line. So this is what we're given. Y is equal to 3x to the 3rd minus 10. So, and then we're given this point here, which is 2 and 14. So what we'll do first is basically just find the derivative of each of these using the power rule. So to solve for this one, we'll multiply 3 by 3 because we have 3 here and 3 here to find the new coefficient, which is 9, which is written here. Then we just bring the x down, and then we subtract 1 from the 3 here in the exponent to get the new one of 2. So that's basically how you do the power rule really quickly. So the derivative of this is equal to 9x to the 2nd, or squared. And so then the derivative of -10, since there's no variable attached to it, that's just 0, so we can forget about that. So we'll just rewrite that here, y equals 9x squared, and here we already plugged in the x point here, which is 2, and solved for that to be 36. And then with that, this is our slope of the tangent line. And so to write the equation for the tangent line, we'll just come over here and plug that into y equals mx plus b, which is the equation for a linear line. So we're given y, which is 14, so we bring that in here. And then 36, which is our slope we found previously. And then 2 is equal to x, which is we just plug in here. And we're solving for b. So this is equal to -72. We subtract -72 from both sides to get -58, which is equal to b. And so just to rewrite that, we have y is equal to 36x minus 58.
All these concepts we've learned, including the concepts of derivatives and related rates, are important because they can be applied in the real world. For derivatives, people can determine the slope when 2 different points are not given. The application of both derivatives and related rates can be used in real-world problems related to physics as well as problems in engineering.